Hey there folks, how you doing? Today we're going to talk about plate tectonics. Plate tectonics is an idea that's been around for a long time, not always under the same name. Very few of you are anywhere near as old as I am. I'm not that old, but old enough for science to change some things. It used to be called continental drift. All right, way back when I was still in high school, it was taught to me as continental drift, even though plate tectonics is definitely older than the late 80s, which is when I was in high school. But, you know, there's always that lag between when stuff makes it into the textbooks and whatnot. So if you were in school in the 90s, you quite possibly heard of continental drift instead of plate tectonics, just like I did. But it's basically the same idea. Plate tech is a bit more scientific. More data, I guess is what I meant to say. So as I said, the idea has been around for a while and possibly even longer. As always with science, you know, you get someone who gets famous for the idea, and there's half a dozen other people that were, you know, working on the same idea. In this case, there was another gentleman who's got some public credit for this, an Edwin Seuss, not the good doctor you guys know and love, but a different Seuss. And so Seuss and Wegener are the two big names here. But way back, I guess 110 years ago now, he put forward the idea that at one point in time there was one giant continent, okay, called Pangaea. And then from there it split into two continents, and then eventually to the continents that we have today. He did some pretty basic just observations. You know, they didn't have the satellite view that we have today, but they were pretty darn good with their idea of what the coastlines of the continents looked like. And I'm sure you've heard this before, the idea that it kind of looked like it fit together like a jigsaw puzzle. Laurasia and Gondwana, I don't want to say we're a bit harder of a working, but well, you'll see in some of the images how it splits up. Laurasia is basically North America, Europe, and Asia. Gondwana being the remainder, what they typically call the southern continents. So there's the idea. And it shows as recently as 65, there's my mouse, 65 million years ago, how different things looked from today. And that's really kind of important when we look at it in the context of, well, not just historical geology, but with something everybody loves, dinosaurs in particular. And you wonder how you get this disbursement of dinosaurs. You know, when they first started, right around here is when dinosaurs began. All right, so they had open roam all over the place. Then, after about 100 million years, basically in the middle of dinosaurs, things had started to split up a decent bit. We opened up a large bit of water in between here, you know, basically starting to isolate these groups. And then, by 65 million years ago, when the meteor impacted over here in the Gulf of Mexico, we see, you know, still some connection. Okay, don't get me wrong, but for example, there still potentially was a land bridge there. You know, this is not the most accurate of drawings we can assume, right? But it's an idea. India had already removed itself. Well, India removed itself a while back here from. India used to be attached, as you'll find out soon, to Madagascar here. India is on its way up to Asia. Okay, things were moving and shaking. Australia, I think that's what I had meant to say. Australia was still attached to Antarctica 65 million years ago. So, anywho, you see what Laurasia indicates and Gondwana. Okay, and when they were assembled, you had Pangea. So, back to Wegener for a little bit. I told you that the continental drift has more data. Continental drift is more scientific. Yeah, but Wegener had everything down, and he had good data. He had fossils, as this drawing indicates here, that when you put the continents back together, he had similar rock types of similar ages, bearing similar fossils. So it's not just that the shape of the continents fit back together like a puzzle, but the actual picture, if you would, on top of the continents fit together. Mountain ranges were another thing that when you reassemble the continents in the way he suggested, without dropping a beat, these what look like isolated mountain chains join together to form longer mountain chains. I don't want to get ahead of myself here. All right, so there's that. So the fit of the coastlines, the rocks, the fossils within the rocks, and then the mountain chains themselves. So the problem was, he had the unfortunate luck, I guess, to say, of presenting this to a bunch of geophysicists. All right? I don't know if that was his choice or if that's how it came out. But you could almost see the name for this theory taking place here. And he explained all this idea, and they just kind of, again, bunch of physicists, they want numbers, math, they're like, okay, Al, this is great. So your continents are sliding around the globe here. They're just drifting through the oceans? How are they moving? What's doing this? And he didn't know. He didn't know how they were moving. All right, he knew, deep down in his heart, however you want to say it, that this is how it used to be. I believe he even had some projected times. Okay, these numbers that we saw back here, I think he had a part playing in this as well. But he couldn't give him a mechanism. And he wasn't exactly laughed off the stage, but this went nowhere. Okay. Unfortunately for him and Seuss. Seuss didn't have much more, obviously, or we would be talking about him. So thanks to those naughty physicists, we just it died in the water back then. But it stayed in the books. We thought it was a good enough idea. I guess it did stay in the textbooks. But again, I'm talking about the 80s. Who knows how long it took to get into the earth science textbooks. So then we started learning more and more. All right, World War II, we learned a lot about the seafloor. We started getting out and about with our submarines and our sonar and whatnot, and we started really just paying attention to the world a lot more. And then even up into the 60s, when we got small submarines that scientists could use, not just the government, things really started changing then. So anyhow, we found out more. We always knew the Earth was layered, at least recent knowledge. We found out more about the crust, the mantle, and the core, and how it all worked. And by the way, as you know from a previous lecture, we go beyond crust, mantle, core, and we go to not just crust, mantle, core, but lithosphere, sorry. Lithosphere and asthenosphere play a big part in our plate tectonics discussion. Okay, lithosphere. I don't know if I've got slides for this. I do not. Lithosphere, just a reminder, being the crust and the uppermost portion of the mantle. I always say just that little bit of goo that you can't shake off the eggshell kind of that much of the mantle. Then the asthenosphere is what we call the middle mantle. It's just below the lithosphere. And it is important to remember that it is not all of the rest of the mantle. There's actually a lower mantle that we don't really discuss. We acknowledge its existence just to remind you that the asthenosphere is in the middle. MOHOROVICIC discontinuity, probably also talked about this, shortened to the MOHO line for everyone's convenience, which marks the bottom of the crust. Professor MOHOROVICIC discovered this, I really got to put a date on that, ways back, okay, using seismic waves, energy, mostly from explosions, okay, monitoring the we'll call them sound waves just for a minute. I guess energy waves would be a good idea, a good word for it. I mean, monitoring the energy waves as they propagated through the earth, and just like your voice, sound, when it travels through air, it sounds one way. When it travels through water, it sounds a different way, right? Same thing is true of these waves. And when they switched rock type or switched rock consistency, okay, they slowed down, they sped up, and they were able to measure that, believe it or not. So anyhow, short story long, right? He identified what ended up being the boundary between the crust and the mantle, between the solid and the not solid rock, which came in right around 22 miles on average. These are both averages, below on land and below the surface, that is, and 6 miles below the seafloor. Hopefully not surprising for you to figure out that the ocean floor crust is significantly thinner than the continental crust. Someone asked me about that one. I said, well, if it wasn't, you'd be underwater, right? But half a joke, half not really. But so the continental crust definitely needs to be thicker than the ocean crust. This is a diagram again you've seen before. It discusses these areas. All right, so I'm going to pause this recording here before we start into a new section here. All right, and we're back. So the idea here behind plate tectonics is that the lithosphere is broken into pieces called plates. All right, and these pieces rest on top of, or what we typically say float, on the asthenosphere. All right, so you've got these solid hunks of rock floating on, for lack of a better word, what we'll call molten molten pools of rock. If you want to picture lily pads, that's fine. A much better example, or a much better image, would probably be cracked ice on a pond, because unless you've got a really densely populated lily pond, I don't know what comes to mind when you visualize a lily pond, a pond full of lily pads. It's probably not dense enough to, we don't have these giant spaces. It's not like a continent is a hunk of rock, and then under the ocean is no rock, and then there's no space again. You see what I'm thinking? It's actually lithosphere under the continent, the lithosphere under the ocean. It's all lithosphere. So there's very few space in between. And since I don't think we have a we don't have a slide that says it. This is a great place to show it here, actually. So these large multicolored polygons, these are your plates. Okay. The vocabulary word I wanted to introduce is plate boundary. Plate boundary. Okay. And basically that's where one plate ends and another one picks up. There's a seam. Okay. And this is where I was talking about the the cracked ice. Usually not a giant gap between them. So the boundaries, okay, is where all the exciting stuff, horrible, scary stuff happens. But also some cool things, as you'll find out. Foreshadowing right here. So this is the idea, at any rate. The lithosphere is broken up into pieces called plates. Those plates rest or float on the asthenosphere, and we've got, 7 or so, half a dozen, I usually say, large plates. Okay, you got the African plate, the Eurasian plate, the Australian plate, the Pacific plate, the North American plate. Did I say Eurasian already? South American plate, Antarctic plate, and then there's a bunch of little ones. All right, and unfortunately, it's these little ones that tend to cause a lot of trouble. Okay, tend to cause a lot of trouble. A lot of earthquakes, often volcanoes as well, happen along plate boundaries in general. And when you get these little plates moving around, I think they move easier. Don't quote me or anything. I'm just me thinking. I think they move around a lot easier, a lot more frequently than these larger plates do. This is a duplicate slide for some reason, and I am going to take this opportunity to get rid of it. I'm not even sure why it's here. I'm sure one semester there was a really great reason I had that there. So I was joking earlier about the continental lithosphere being thicker than the oceanic lithosphere. It's not just thickness that keeps us above water. The continent is actually made out of different material, different rock, than the ocean crust is made out of. Continents are made out of basalt. I don't know if I get into that here. Yeah, I do. I said that backwards too. The oceans are made out of basalt. The continents are made out of granite. All right, and you don't need to remember these numbers right here, but you see that granite is a little less dense than basalt is. All right, and as such, granite would float. They were both liquids, both moltens, and even when solid, apparently. Granite floats on top of basalt. All right. That isn't what I meant to say. That isn't what I meant to say. Granite doesn't float on top of basalt. Granite doesn't sink as much. I'm trying to think of there's a barge metaphor in the back of my head about an empty barge and a full barge coming back, and the full barge sits lower in the water than the empty barge. Okay, and basalt is the full barge. All right, it sits lower in the asthenosphere than does the granite. Okay, ignore what I said about granite floating on basalt. I don't know what I was thinking, but just in general, the rock is less dense, so it sits up higher in the asthenosphere. So this is another reason why the continents are higher. Okay, sit higher than the ocean floors do. And not to mention, of course, that because the ocean floor sat a little lower, that's where the water pooled up, right? And once you get the weight of all that oceanic water on top of it, it pushed the oceans down even further, the oceanic crust, and which buoyed up the continental crust even more. So there's a lot at play here. There's a lot at play. All right, as I indicated a couple moments ago, after that rather awkward slide we just had, there are a handful of things that plate tectonics is responsible for. Plate tectonics is responsible for the majority of the earthquakes that we have. There's other reasons for earthquakes too, but typically plate tectonics. Plate tectonics is responsible for the majority of the volcanoes and mountains. that we have. Again, there's a few other ways to get these things, but primarily, and plate tectonics is also responsible for the current location, orientation of our continents. Plate tectonics has really been an interesting thing to watch over the years in geology, and even in the 20 years that I've been teaching, it's changed so much. Basically, on the teaching side of things, it used to be the absolute last chapter in the textbook, and which is still the way I teach it, really, almost. We go through the whole semester, talk about all these individual things, earthquakes, volcanoes, mountains, so on and so forth. And then at the very end, we say, oh, and hey, by the way, remember all that stuff we talked about? Well, here's what's responsible for it. All right? That's an older, more traditional way of presenting it. Nowadays, if you notice, plate tectonics is probably way in the beginning of your textbook. Okay, one of the first couple chapters typically. I'm not so sure about the earth science book, but in geology textbooks, it's definitely way up there. Okay, and the idea there is to say, okay, here's this grand idea that ties everything together, and we're going to spend the rest of the semester talking about various bits and pieces of it. And as I said, I kind of do a hybrid of that. Okay. I've mentioned plate tectonics all along. I've given you bits and pieces of it as we've gone through. And then at the end, well, then we talk about it in depth. And there's actually a great reason for that. I often don't, one thing or another, don't have time to do the entire plate tectonics chapter. But because it's so important, I make sure that I squeeze it in wherever I can throughout the semester. And hey, it never hurts to hear about stuff more often than less often, right? So I like to think I do a happy medium between all of that and honor everybody's point of view about its importance there. All right, so plate tectonics is important. Earthquakes, volcanoes, mountains, continental location. Got it? Good. As I said a couple minutes ago, several large plates, 7 large plates, several small plates. This is new here. They move from 1 to 18 centimeters per year. Move in various directions as well. This is still quite befuddling. They move at different speeds. If you're having trouble picturing 18 centimeters, remember there's 2.5 centimeters to the inch. Okay. So that might help you ballpark how many inches we're looking at here. But there's a wide variance here from 1 centimeter to upwards around 10 inches. Big difference. Let alone north, south, east, west, northeast, southwest, whatever. All these varieties of directions. And thinking back to that broken ice on the pond, it's not exactly a bumper car game, okay? But some continental plates do seem to have a little more freedom than, some plates, not necessarily continental, some plates do seem to have a bit more freedom than others. India is a great example. We told you that it ripped itself off of the side of Africa, over by Madagascar, turned itself completely around, and has been trying to jam itself up into Asia for the last 60 million years. Okay, and that really doesn't necessarily represent any movement that any of the other plates are doing. It's just doing its own thing. Going rogue, I guess, as they say nowadays. So there's still a lot to sort out in here. The way we'll present it in a couple minutes, you'll understand how and why the lithosphere moves on the asthenosphere. But directionality, speed, they're still working on that. So again, these plates, okay, maybe make a little more sense to you now. And this is also weird because North America's not in the center. That always weirds out Americans when we look at a map. It's typically, we're right dead in the center, aren't we? So North America's all the way over here. Here's the Atlantic Ocean. Here's the rest of the Atlantic Ocean. Coming over here now. The rest of the Atlantic Ocean. England, Spain, Europe, whatever you want to call it. All right. More Atlantic Ocean. Off of Africa. More Atlantic Ocean. Off of South America. Okay. A little plate here in the Caribbean. Very important. Every time poor Cuba gets an earthquake, here you go. The volcanoes in the Caribbean. There you go. Okay, if you stop and think about it, plates can basically move three ways. They can move towards each other, they can move away from each other, and they can slide side by side each other. And I think those three options apply to just about anything in life, not just plates. Okay. Unfortunately, because you have two different kinds of plate material, continental and oceanic, right? This turns into like 6 things that you have to remember. All right. It might even be 7, I forget. What happens when plates move towards each other? What happens when plates move away from each other? Varies on what kind of plates you're talking about. All right. And you guys, unfortunately, need to remember what happens when these plates do this stuff. And again, lastly, this is responsible for earthquakes, volcanoes, and mountains. Okay, so we'll stop the recorder here, get my mouse arrow back, and we'll start up with all of these neat things you have to remember.